Okay, in this video we're gonna go through the last two types or the last two classifications of crystalline defects, which are 2D and 3D defects. So 2D defects are called plane defects or planar defects, and they happen on planes or on surfaces. So the most common type of plane defect is called the external surface. Okay, external surface simply refers to, let's say you have a piece of material. External surface is just literally the external surface. Okay, so this is the most common type of 2D defects. So what happens is atoms on the surface are bonded to other atoms on only one side. Okay, so on the surface, the material, so let's say these are the atoms on the surface, it's only bonded to the atoms underneath it. Okay, and of course the atoms on the side, but when you're talking about the whole plane, then it's only attached to the plane of atoms underneath, whereas at the top there's literally nothing here. Okay, it's whatever that's on the surface is open to the environment. Right, so higher energy associated with these atoms makes the surface susceptible to reaction. Okay, I think this is very logical. Okay, it's not easy to, it's not difficult to understand. Whatever that's exposed to the environment will be affected. Okay. Now, another type of plane defects is called grain boundaries. Okay, so you've seen this term before. Grain boundaries are whenever a nucleation happens and then the nucleus forms into crystals, and the crystals eventually meet and something called boundaries or grain boundaries are formed. Okay, you've seen this in the earliest part of the chapter. Okay, so these are grains. The empty spaces are grains and the lines are grain boundaries. Now, grain boundaries is actually can be considered a type of defect. Alright, so what it says here is a narrow region between two grains of about 2 to 5 atomic diameters in width contains mismatched atoms from the adjacent grains. So while the crystal can perfectly grow, okay, the nucleus grows into crystal and the crystal can perfectly grow into a crystal structure. But at the point of the crystal meeting each other, okay, two crystals meeting each other, of course this region can't be perfect. So the grain boundaries are actually a region of size 2 to 5 atomic diameters. Okay, and here contains mismatched atoms. So you can't get a perfect FCC, BCC, etc. arrangement on the grain boundaries. On the lines, you can't get a perfect arrangement. If it were perfect, there won't be any boundaries. It will just be one smooth arrangement like this. But this is not possible because we have nucleation happening at various sites, which causes many crystals forming, which then causes the grain boundaries. Okay, so what it does physically is it separates the grains that have different orientations. Okay, so this nucleus will grow into crystal of this orientation, and then this one will be different orientation, etc. So the boundaries separate the grains of different orientations. You can see that in this diagram. Okay, so of course we know that the grain boundaries are formed because the crystals are simultaneously growing at the same time. Okay, we learned this from the solidification topic. So favorable sites for nucleation and growth of precipitates. So because of this irregularity, because of the existence of these boundaries, they become favorable sites for nucleation to happen. if nucleation hasn't completed yet, and for growth of precipitates. Okay, I think you can appreciate this point. Whenever there's some irregularity, this is where unwanted things will form, right? Okay, so irregular atom arrangement provides lower atomic packing and high energy. So this is how it affects the entire arrangement, and atoms are thus able to diffuse more rapidly to form precipitates. So the irregularity is affecting the arrangement. It's reducing the density, it's making the structure has less integrity. So the atoms there are quite free and they're able to diffuse and react and hence form precipitates. Okay, you can pause if you want to look at this diagram. Actually, it's just a cuboid. Okay, here there shows the complete volume of the grain, and where an edge is being shared by 3 grains. Okay, so and a boundary is being shared by 3 grains, and this face is being shared by 2 grains. Right, we also have vertex, which is the point where 4 grains are sharing. Okay, so this grain boundaries, which is what we wanted in the solidification process, is also a type of defect. Okay, so you can see the grain boundaries under the microscope in this diagram. Okay, physically we can see the lines here on this diagram. Yeah, so these are the grain boundaries. This material here is 1018 steel. Okay, so another type of plane defects is twin boundaries. We know what twin is, right? So this is a region where a mirror image of the structure exists across a boundary or plane. Again, this boundary or this plane is imaginary. It's not physically there. Okay, so what happens is that you can see that on, let's look at this line, for example. Okay, on this line, if you were to take this portion, you can see that this line is mirroring these 2 sides. Okay, this is the plane of mirror. Okay, so twin boundaries is wherever there's a mirror image of structure, then it's called twin boundary. Okay, this defect is formed during the plastic deformation process. You might not be too familiar with this. This is when you deform a material that it cannot get back to its original shape. We'll learn more about this in chapter 5 and 6. And also during recrystallization process. Recrystallization is when a solid metal is heated and it becomes soft, and crystallization is happening again. It's not completely melted, but it is becoming soft. Okay, you'll learn more about this in chapter 5. What this does is it strengthens the metal. So not all defects are bad. Actually, most defects are good. They are contributing to improving the material's structure and properties. Okay, the final type of defect is called volume defect. This is the last classification, or 3D. Okay, there's nothing extra about the 3D. It's just a cluster of point defects joined to form the 3D void. So remember, point defects, you have your vacancy, Schottky imperfection, etc. So this is when those defects are close together and they form a 3D void. So if there's just one of it, it's point defect. But if that defect is gathered in a region, it's considered a void. Okay, a 3D void. So some scientists refer to grains as volume defects. So you see how this is quite subjective. Remember grains? Okay, we have a whole, let's say, material here, and the grains, just like what you saw in the previous diagram. Okay, so let's say there are grains here. So some scientists even refer to the grains that are formed as a defect. So grain boundaries are defects. The grains also can be defects. Okay, so that's it for this topic. Make sure you carry out whatever tasks or assignments that is posted after this video. See you guys.